Hello, everyone. This is Elisa Baum, and I'm GridGain Systems Senior Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct a bit of housekeeping. First, could you please raise your hand using the hand icon located in the control panel to let me know if you can hear me. So I'm going to go see if you guys can hear me. Can you hear me? Let's see here. Yep, it looks like people hear me. Next, during this webinar, you will be on mute, but should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible. And in addition, a recording of this webinar and the slides will be made available to everyone within 48 hours. So with that said, I'd like to introduce today's speaker. It is Rob Meyer, and he is GridGain Systems VP of Product. And with that said, I will turn the floor over to his presentation of options for adding speed and scale to MySQL deployments. Rob, you have the floor.
Thank you. Morning, afternoon, and evening, everyone. I'm Rob Meyer. If you cannot hear me, speak up, and we will try to fix it. Elisa, you can hear me, is that correct?
I hear you.
Okay, perfect. So today's session is going to be all about MySQL, or as it used to be called, MySQL, since it was named after Monty's daughter, I think. So we'll be talking all about adding speed and scale to MySQL database deployments and all the various MySQL and third-party options out there that are getting used today. One of the reasons we started doing this whole series is there don't seem to be reference guides for MySQL or Postgres or Oracle. So we actually started creating them because we were being asked all those questions. So if you have questions about this one, we'll go through it. We're going to give you a white paper, send you a white paper a few days after so you can go through it in more detail. And if you have questions about some of the other databases like Postgres, or PostgreSQL, or Oracle, you can find those white papers, those guides out there as well. But let's get started with MySQL. So MySQL was founded as a company 25 years ago. It's hard to imagine so that it's been out that long. But over the years, there's been a combination of innovation, followed by consolidation, followed by more innovation. So the first round started right away with clustering, with trying to add speed and scale. So Alzado was a VC-backed company out of Ericsson that focused on adding scale to MySQL, so horizontal scale out MySQL for telco grade applications. MySQL acquired it in 2003 to start to add the clustering technology into core MySQL. Oracle, in the meantime, has always had a tradition of buying other databases and consolidating. They bought InnoDB, which is the current MySQL storage engine, the de facto storage engine for MySQL. They bought that back in 2005. And then between that time and when Oracle swallowed MySQL, a number of innovations happened around scale out. Percona started, they're one of the great open source services and product shops out there. They released Percona Server for MySQL, which is XtraDB today, that went GA around 2006. Clustrix, one of the horizontally scalable scale out MySQL databases, was started in 2006. Codership released Galera Cluster, which is kind of the de facto clustering technology outside of Oracle MySQL, that came out in 2007. And then the consolidation happened. So MySQL MySQL was swallowed by Sun in 2008, which was in turn swallowed by Oracle in 2010. The day that acquisition closed, the innovation started. So MariaDB decided to spin out that day. Monty and a core part of the core team of MySQL started up MariaDB. And while the clustering options evolved both with MariaDB and with Percona, a couple other options started coming up for scale out. And in 2018, MariaDB acquired Clustrix. So we can expect more innovation around write scalability and horizontal partitioning of the data, but that's not really the only way to fix this. In fact, it's not going to address all the problems with speed and scale that are hitting MySQL and are hitting other databases. And so if you get nothing else out of this session, I want you to get that one thing, that it's not just about the database. You're going to have to be looking at why these challenges are happening where MySQL and other databases are getting overloaded so quickly, where vertical scalability and the existing technologies just aren't enough anymore. And what's really been happening is as digital business, as the Internet of Things has started up, it's put an incredible load from the outside in on companies. So as we built the apps, which became legacy apps, the definition of a legacy application is an application that actually gets used. So as these legacy apps started getting adopted and then integrated through middleware, and then eventually exposed through middleware to APIs, which then had layers of APIs, which then had layers of security to protect those APIs, which then got integrated with cloud apps, which then, or databases as a service, which then eventually got consumed by mobile and web apps. All those layers have been putting an incredible load on the existing systems. As much as if you look at various analyst reports, if you talk to customers who are using MySQL, as much as 10 to 100 times increased queries and interactions and transactions over the last decade. And it's not just about the load on the existing systems. The amount of data people are actually consuming is up about 50 times. It's not the transactional data, which is up. It's more data like social data, machine data, data from click streams. That's what's been growing as much as 10 times in the last 2 years alone. And so that's putting an incredible load on databases that have to scale to support much larger data sets. In addition, what used to be traditional ETL and OLAP analytics, where the data could be stale, that's been changing and moving more towards real-time analytics as people try to service these new channels like web and mobile apps and do things like real-time personalization or real-time recommendation engines, or just catch people having bad support issues and try to fix them as they're happening. All of that requires real-time analytics, which is literally taking analytics down from hours or days for when you get reports to seconds. And traditional warehouses can't do that by scaling up vertically with specialized hardware, no matter how hard they try. And technologies like Hadoop, which are great at batch, are not as good at real time and are relatively complex technologies to manage on their own, which we've seen even in the market in the last year or so. So these are the challenges that are hitting everybody that we talk to. And you can kind of boil it down into 4 problems. The first one really is just to handle that speed and scale, you can't just scale MySQL vertically with hardware. It doesn't work because the hardware can only grow as fast as Moore's law. You know, maybe it doubles every 18 months if you're lucky, but it doesn't grow 10 times in 2 years. Second, if you're on a mobile app and you expect sub-second responsiveness every time, it doesn't matter how fast you make the database, you also have to cut all the latency even beyond the legacy app, the layer of middleware, the layers of APIs, the 2 layers of security you might have for threat protection and then for authorization and policy management. All of those layers add latency to the point where the API needs to be 100 milliseconds or less usually, the one receiving the request, which means there really is no time to access all those middleware layers and get to MySQL, which means you have to do something outside of the database and the application. Even if you fix those problems, there's an issue with flexibility too. most of the internet startups, the new entrants into businesses, when they deliver new functionality, they do it in days. They change APIs in days. And for an existing company, to do that is almost impossible unless you figure out the right architecture where you can make changes to APIs without having to make changes to your apps, because your apps do not change in days. They're months or years. It's just the reality of how they're built and how you release them. So you have to figure out how to do that as well, release in days, and be a lot more flexible to change. And then the final thing is, how do you do the real-time analytics? So that's not easy, because you can no longer rely on an ETL pipeline and stale data to do your analytics. You have to somehow figure out how to do analytics against the live data in the existing apps. And most databases are not, most OLTP databases do not work well for OLAP, and they weren't sized with their existing apps or designed with the existing apps to handle OLAP and transactions in the same space, in the same, during the transaction or the interaction. Some people call that hybrid transactional analytical processing. It's a whole new field. And so you have to figure out how to address real-time analytics and decision automation as well. How do you add things like machine or deep learning to automate some processes like one-click shopping to make sure that it just gets done? Not so easy on the existing applications. So you have to figure out how to do it outside of the applications. So I said, remember one thing, that the speed and scale issues are not just with the database. Anytime a database is falling down, you can't just necessarily fix it by fixing the database. So if I ask you to remember a second thing, hopefully you do, which is always ask the whys. In just-in-time manufacturing and continual improvement, we always used to call it the 5 whys. So why is the database falling down? Well, because there's a load coming from this middleware. Well, why is the middleware getting overloaded? Well, because it's coming from an API. Well, why is the API getting overloaded? And you keep asking the whys until you find the root cause. This is an end-to-end system design problem, and the system goes all the way out to those web and mobile apps. You have to design for that, just like we always had to design for any system end-to-end for speed and scale. So go look at the end-to-end problem, think about the many projects that you might be doing end-to-end, piece together a roadmap for what makes sense, and then work your way back and ask yourself the question, if I invest in MySQL today, how is it going to hold together and solve some problems for the long term? So for example, don't just invest in scaling up with expensive hardware to scale up MySQL, because you may have to throw that hardware away a year or two down the road because it hits the wall. Go ask those questions now. So we're going to start by looking at the options within the MySQL community, which is actually larger than what many people may realize. So we're going to look first at how you lower latency. What are your options for lowering latency or adding speed to MySQL? Then we're going to go into the longer list of how do you improve scalability, read and write scalability, as well as data set or data size scalability. It's going to be focused mostly on OLTP because honestly, you can't do both with the same solution. We will talk a little bit about what some options are for adding OLAP kind of scale or columnar kind of technology. And we're also going to talk a bit about cloud, which is really MySQL as a service done well. And so if you are considering a migration to the cloud, you probably want to start looking at some of these options now as part of your longer term planning. Let's talk about adding speed. So first, you can just throw RAM at the problem. You could add a RAM disk. You could add SSD or SSD accelerated by Intel Optane, and it just looks like a file system, and you can get some good performance out of that. If you haven't been trying that, that's probably a relatively easy thing to look at. You may be looking at different spindles or different disks for different things like your write-ahead log versus your main tables. easy, it's an easy win. The other thing that people often look at are memory tables. I personally cannot recommend this one. It's typically used for temporary tables. It's not persisted. It doesn't work with clusters. And there are various limitations. SQL Server has some similar limitations in that. It doesn't just transparently work. In the case of MySQL, you've got, it doesn't support foreign keys, which is a problem. And transactions aren't really going to work, along with concurrent access, so MVCC, concurrent control is not going to work in this case. And so if transactions are an issue, you're probably not using memory tables. It's also concurrent writes. In core MySQL only locks at a table level. It doesn't lock at a row level. So you can get conflicts pretty quickly, or collisions pretty quickly. I included the link here in case you're interested in looking more at the storage engine and the memory tables for your reference. Memcached is probably the most widely used cache with MySQL. It's documented within MySQL on how you set it up. For those of you not familiar with Memcached, it's a cache-aside cache, meaning it's a cache you bolt onto the side of the application, where you have to change the application to populate the cache and to pull from the cache as you need data. So the application manages, whenever it goes and accesses the database, am I going to access the cache first because I think I have a copy, or do I need to go through the database and do a read and get it and then populate the cache? It's managed by the application, which doesn't have complete control over the database. So the application doesn't know if the database has been written to by someone else, so it needs to guess. So the application needs to manage whether to refresh the cache and pull new data and get the most recent copy. It does help with latency if you can have Memcached on the same machine as the application, if you have the available RAM. When you run out of the available RAM, you're typically, as with other caches, going to move Memcached to a dedicated set of servers, in which case you're going to access the data over the network. In that case, the network can become a bottleneck. You have offloaded reads from the database, and if the database is overloaded, your response from Memcached is definitely going to be faster. But if the data sets get so big that the network becomes the bottleneck, then you're in trouble. That's actually not that unrealistic. It's happening more and more because a network can really move only a gigabyte a second. So if your application needs a gigabyte or more, it may have to wait a second or more to get that data. And as we can see with some kinds of web and mobile apps, a second is too long. So you may have issues where Memcached doesn't really scale with large data sets, where you might have to partition the data, and Memcached is hard to manage with partitioning or with the network. Redis is another solution. This is probably the second most commonly used. It is better than Memcached as a technology. It still has some of the same issues. It does shard or partition. You can do it. Most people, when they get to scale, end up managing partitioning on their own for other reasons, which we'll go into later. But it's not so easy to partition data. And you can't run the compute with Redis either. Generally, if you're going to scale Redis, you're going to do it on a dedicated set of boxes over the network. So you have to fetch the data over the network every time and move it to the app, to the compute. So the network is still a bottleneck. Those are really all the options for lowering latency, with one exception. I probably should mention thread pools. This is something you need to look at. Core MySQL does not have thread pool capabilities. MySQL Enterprise Edition and Percona actually does. Percona offers it for free, so we'll go through that later when we talk about Percona. Thread pooling is something where you can use it to optimize concurrent reads and writes. So that is an option for lowering latency, but not directly with memory. For scaling, if there's one thing I heard from other people I talked to with MySQL, it's that sharding comes last. Partitioning is your last resort. You try everything else first because partitioning is the hardest one to manage. While that's getting better, and we'll talk about some of the options that make it better, that is still generally the case if you're sticking to your existing distribution of Oracle MySQL with InnoDB or Percona or MariaDB, meaning InnoDB, the InnoDB equivalent at MariaDB. So what are your options for scaling horizontally? Well, in general, the replication that exists with MySQL is read and write replication, but it's more focused on scalable reads. And what I mean by that is group replication, which is the technology that got rewritten that most use. It does synchronous and asynchronous replication. And it is a read, any node, it replicates the entire database to every node in the cluster. Every node can handle a read. Every node can also handle a write. And the writes get coordinated across the nodes. And so it is a shared something architecture in that all the writes have to be coordinated across all the nodes, and the resources to do that increase exponentially with the number of nodes. So what that means is your shared something architecture, where they share the state of all the writes, limits your scalability for writes. The other thing that's interesting is none of the replication-based solutions really do sharding or partitioning. And that creates odd behavior sometimes when you've done your own partitioning and then you're trying to use group replication and cluster, InnoDB cluster, where the writes lock up the servers and you have to manually restart them. It can also lead to weird issues where if your secondary crashes, your primary, but your secondary, you don't actually have a way to recreate it automatically. You actually have to go manually recreate your backup, your secondary servers, and that's a problem. So partitioning makes things more complicated. The other thing is, once you partition manually, it's not just that you partition once, you often have to rebalance. And partitioning has to be done for every workload as well, meaning different applications use data in different ways. And to minimize the network fetching across nodes, you may actually want to create copies of the data or replicas on the other nodes. So there's a combination of partitioning and replicating or copying data that you need to manage, and that makes it really complicated really quickly. We'll talk about the cloud offerings, but they don't solve the partitioning problem. They're really the same software as a service that's on premise. So you generally are going to consider the cloud if you're migrating to the cloud. And in that case, there are great offerings from Amazon, Azure, and Google, and whichever vendor you choose, you're probably going to have a good MySQL option, but it's going to be the same. Same challenges with scaling and write scalability and dataset scalability that you have on-prem. There are various OLAP offerings that exist as well, but they're separate. So, one of the ones that comes up from time to time is Memsql because it is MySQL client wire compatible. However, it really only handles OLAP, not transactional systems at scale. And so again, you'll quickly get into a situation where you'll need to have your OLTP-based MySQL stack, however you're scaling it, and then you're going to pipeline the data into an OLAP stack for handling OLAP at scale. And that's what everybody does, with one or two exceptions that we'll go into. So let's go through some of the options right now. The main one is MySQL InnoDB cluster. And when I talk about the different options, I don't think it's important. Well, I don't think it's enough to talk about the database distribution itself. You've got to talk about all the clustering technology on top that makes it scale. So that's what we're going to focus on here. And within Oracle MySQL, there's MySQL InnoDB cluster, which consists of the MySQL router that was rewritten for MySQL InnoDB, MySQL shell, which is the admin console. You have to add that on. It's the admin API that helps you manage the cluster. Core group replication, which is now 3 years old, and the InnoDB storage engine, which is now the de facto storage engine, we're not really talking about ISAMDB anymore. And we'll talk about the other storage engine, the Alzado storage engine later, which is MDB. So InnoDB has become the de facto. It has a 64 terabyte limit. And on top of that, you have replication and you have routing on top of the different replicated instances for routing requests to the whichever server you decide to route it to. MySQL group replication is single master or multi-master. Single master by default, you can turn on multi-master. One of the reasons they rewrote it was to come up with a better consensus algorithm for coordinating the writes. They use Paxos. They're not the only ones across the database community for majority consensus. So not all of the nodes have to agree to a write. Once they agree, they commit. If they don't agree, then you have to roll it back. And it can take time before they disagree, especially if there's some kind of split brain scenario that happens where they disagree, and that creates a split brain. So they support synchronous or asynchronous replication in those cases. Synchronous would be obviously the most pessimistic version. Even with the most pessimistic version, though, you basically are in an optimistic architecture, optimistic transaction architecture, where if a conflict does happen for any reason, you probably have to put in a rollback, some kind of compensating transaction in addition to the rollback to get the data back to a consistent state. Group replication does have failover. However, it does not work properly in all cases with partitioning. So if you've added partitioning, then you will end up in cases, and hopefully this gets fixed over time, it usually does with technologies, where you have to restart a node manually. So you have to be aware of that with MySQL and InnoDB cluster, that with partitioning, it's going to be a little bit more of a headache, hence why people say try partitioning last in the MySQL world. MySQL InnoDB cluster also is not really a WAN solution, meaning it assumes low latency and high throughput for its connections. So that's not good for a WAN. So that is another current limitation. You would expect that to get fixed over time. There are really three additions to MySQL. There's the open source MySQL, there's an enterprise edition, which is really what we're talking about here. If you're going to get the clustering, you have to get enterprise edition at the very least. And then there's MySQL CGE, which is the sort of the clustered edition we'll talk about next. It works for both InnoDB and the other storage engine, InDB and InnoDB cluster. And there are a couple extra features you get that can help with WAN-based replication as well. That's $10,000 a server, so that's twice the amount. The other thing is flow control, which I thought was interesting. Flow control is managed by each node within InnoDB. It's not managed centrally, which means you can get into edge conditions. Even if the local nodes understand what all the other nodes are doing, generally flow control works better when it's centrally managed. All right, so that is MySQL. You want to go to mysql.com or look at the Oracle website for MySQL for the enterprise editions. You can find more information there. Oracle has two versions of MySQL, really. There's InnoDB and the open source MySQL. And then there's the Alzado technology that was for enterprise grade telco deployments originally, the one they acquired in 2003. It has a separate storage engine, which gets to 128 terabytes per limit per engine. And on top of it, NDB cluster does auto sharding or auto partitioning and rebalancing across the cluster and automatic replication. It does work. It is proven. It is designed for 5 nines, and it gets 5 nines or less than 5 minutes of downtime a year, in part by making sure it can usually fail over recover within 1 second if anything goes wrong. It does synchronous replication within the cluster, which is great, good pessimistic replication. It does asynchronous across clusters clusters, which you'd expect for LAN-based replication. It's twice the amount of Enterprise Edition, and it's not really MVCC. It doesn't really do concurrent transactions. It supports read committed level only, not repeatable read, not serializable. Okay, and read committed means basically you could get dirty reads. So you lock on write, not on read. And that can be a problem with certain types of transactions. So if you need transactions to support things like exact inventory levels, exact account levels for payments, this is probably not the answer. Outside of MySQL InnoDB cluster, there is Galera cluster written by Codership and released back in 2006. It is for the InnoDB storage engine primarily. It can be used with multiple load balancers. It can be used for MySQL, it can be used for Percona, and it is, and used for MariaDB as well, and it is for that one as well. It is the de facto clustering, at least there's a different version of Galera for MySQL, Percona, and MariaDB. They all use their own routers, so there are several you could look at, including Proxy SQL, which is Percona and really MySQL, and outside of InnoDB cluster, and MaxScale, which is MariaDB's solution. It is multi-master replication by default. You can dial down, dial up the number of write servers, so you decide how you want to manage that. It uses certification-based replication, where a write set is assembled and sent to all nodes, and if they all agree, it commits. If not, it fails. You know, it's just like InnoDB cluster. It manages, it does automatic failover, it does the split brain prevention. The flow control is better in that it's managed centrally, and it does provide WAN support, so it does do things like filtering across the WAN. The challenges are somewhat similar as well because it is a shared something architecture, a multi-master architecture, basically. It's limited by how much it has to, how much resources it has to throw at and to manage an increasingly large number of nodes, an exponentially larger amount of resources to coordinate the increasing number of nodes it has to coordinate across. So that's a challenge. It's still really, there are edge cases where you would need compensating transactions and the partitioning is still manual. However, the partitioning does, once you've done it, it does actually work well with the clustering software. So, and you'll see as we go through some of the distributions that there's some optimizations that work reasonably well. MariaDB is the first other distribution we'll go through. It uses Galera. As I mentioned before, it was founded in 2010, the day Oracle completed its acquisition of Sun, and on adding new features. The good news is there's innovation. The bad news is it leads to some incompatibility across MySQL and MariaDB. So it's not just a drop-in replacement, and that's just going to continue to be. There is one major feature, which is the column store option that you can use with MariaDB for better OLAP performance. So the way this works in the full MariaDB cluster setup is you have MariaDB for OLTP. You then have MaxScale, which is the router that also does change data capture and pipelines the data into MariaDB with column store. And then on top, you have, on top of the Galera cluster that's being used for managing all these engines together, you also have MaxScale as a router. Okay, so MariaDB does have its own version of Galera cluster. They include it in. You can also get MariaDB cluster from Codership, and they do add their own integration. In general, it's nice when the vendors add their own integration and optimize everything together. It's less of a headache for you. So in general, this is a good thing, both with MariaDB and with Percona and with MySQL, with Oracle MySQL with the Enterprise Edition. Some of the challenges are, again, still shared something architecture, still not doing automatic partitioning, and still have the automatic transactions. Your choice between MariaDB or MySQL or Percona even is going to be more about the feature differences. The performance and scalability options, especially with Galera being having better speed and scale optimization than InnoDB cluster right now. Your choices are going to be more at a high level about the features you're getting in MariaDB versus some of the other distributions. Percona is, in every ecosystem, you seem to have at least one of these shops. Percona is an open source shop with a bunch of experts who not only know MySQL, but they know all the different distributions, and they'll support the different distributions, you know, MySQL and MariaDB and Percona's distribution, but also they work on PostgreSQL, they work on Mongo, so they're general database experts. In fact, they'll even benchmark and analyze some of the other options we'll go through down the road. So it's nice to have a shop like that to come to just get advice on the best options, because they're a little less biased than one particular software vendor. They will work and they show it openly. So I think Percona is a great source for information just to analyze what options you have. Back in 2006, they released what's now called XtraDB, which is the Percona server for MySQL. What they do is they basically created a free drop-in version of MySQL Enterprise Edition. So if you were just looking at open source MySQL versus Percona XtraDB, it's hard for me to say why you wouldn't choose XtraDB, to be fair, because they've added things like thread pools, a good implementation of thread pools, and a whole bunch of other features that you only see in MySQL Enterprise or some other enterprise licensed version of MySQL. They focus on performance, they focus on improving scale, they focus on visibility or monitoring and management as well. So you can look at the detailed feature comparison. I decided to include a link, but they take pride in adding all these things. They'll even merge in features from other databases into Percona just to get the best combined into the Percona MySQL distribution. They originally were using Galera cluster and I think licensing it, but when Galera went open source, right around the time Red Hat was looking at it for their distribution, Percona took their own, they created their own open source version and started optimizing it. So XtraDB cluster is basically Galera with optimizations from Percona. And then Percona also includes Proxy SQL as part of their full solution. It's not a plugin, it's not an add-on, it comes with it. It's part of XtraDB cluster. Proxy SQL is solid in performance, got some great security options, and they've got some interesting features like ID routing that keeps routing the same requests, repeating requests to the same servers, which is actually a great feature for things like partitioning and making sure that that things always get routed to the right partition or partitioned server instance if you do manual partitioning. Again, similar challenges around the shared something multi-master architecture, similar challenges around transactions that you can't really do a full pessimistic transactions. There are cases where you might have to do a compensating transaction. And manual partitioning, but it does, like MariaDB, it does, because it's Galera, work well with partitioning. There are a few more that are more distributed SQL now. The first one is Vitess. It came out of YouTube back in 2010 when they were trying to solve their MySQL sharding issues. It was one of the first projects, I think one of the first overall to support Kubernetes. So they made it container-based really early on. And then what they added was automatic sharding and rebalancing, and doing it in such a way that's completely transparent to the application. The application thinks it's dealing with a single database. So it is a shared nothing architecture in that it's single master for each shard. There is, similar to Apache Ignite actually, or Cassandra, there is a single, sorry, not Cassandra, but definitely Ignite and Vitess, single master for each shard. So writes can go anywhere where there's a replicate, where there's a copy, or the master. The master, there's only one write. And if you do that right, if you figure out how to partition right, it's true linear horizontal scale. It shards using multiple keys, what they call sharded materialized views, which means that you have at least a shot at supporting multiple workloads. It does not have user-defined sharding, which would be the next step to make sure that you could shard even better and minimize the network fetching between nodes for data that's missing in a particular node. It is still maturing as a technology. It's important to understand that, particularly with Vitess. Great technology, still a little young. PlanetScale, which is a commercial entity that's contributing to Vitess and providing support and offering commercial versions, they only started a year ago. The Cloud Native Computing Foundation made this the 16th project in 2018. That's only a year ago. And the early adopters have mentioned, Slack in particular is one of the earlier ones, it needed to change to support their needs, which were slightly different from YouTube. So you need to evaluate this one carefully. It is proven, it is running at scale in some really smart shops, not just Slack and YouTube, but some other really smart shops. They are smart shops, okay? So you need the talent that knows how to use this stuff, and you need to evaluate to make sure none of these limitations are really going to hurt you. There's an FAQ where you can check out the limitations and see if that's an issue. If you're doing a container-based architecture, this may not be a problem, but in general, people like out-of-the-box monitoring, and the traditional MySQL-based monitoring is not really supported. Several Nines is one of the third-party vendors. They don't really work with Vitess yet. And then Orchestrator is often recommended for managing the masters. That's Vitess. There's also Clusterix, which MariaDB acquired in 2018, so less than a year ago. It is a true drop-in replacement for MySQL. It is not MySQL, okay? But it is truly a drop-in replacement in code and API compatible. It's just that it's written in C. There's no shared code base between MySQL and Clusterix. It is true linear, horizontal, shared nothing with automatic sharding and rebalancing, meaning single master architecture. That's the only way you really get linear horizontal scale. It does enforce MVCC. It does do pessimistic locking with a two-phase commit. You need to understand you need both pessimistic and optimistic locking, because pessimistic locking is expensive. So you do it as almost as a last resort, but you need it. But it does have it. It does support read committed and repeatable read. It does not support serializable for an end user. It does actually use serializable for synchronous replication, which is quite impressive. So this is a solid, hardened, proven solution. It's not going to lower latency. It is not an in-memory database. So if latency is a big issue in the database, you may be looking for something else. You may be running this on expensive SSDs, for example. Or you may be increasing the thread pool memory sizes for caching. The other challenge is it's only about the database. It's not going to solve challenges with the network being the bottleneck between the database and the applications for very large data sets. For that, you're going to look to other technologies. And you're probably not going to look to the cloud for that as well. As we talked about before, Amazon and Azure and Google all have great options for MySQL, which is basically MySQL, the same MySQL as a service. You have Amazon Aurora, which does things slightly differently. It is MySQL and PostgreSQL compatible. It delivers better performance overall at about a 20% premium, if you ask folks like Percona who benchmark these things. It has some limitations in performance in other workloads, very specific things like second-level index updates. It struggles in comparison to something like Amazon RDS for MySQL, but for the most part, it's better performance. It is basic group replication, read replication, which coordinates writes. It has the same scalability limitations and other limitations as on-premise MySQL. And all of them do. I think the way to think about this is you can make a bet on any particular vendor for your cloud strategy, Amazon or Azure or Google Cloud. MySQL is not going to make the difference there. You're going to have a good enough MySQL deployment to survive. And if you need something else outside of their offering, you can always go to a container-based architecture for things like in-memory computing that can scale even further. So regarding those third-party options, there are a number of them. In-memory computing is something that gets used quite a bit. The most common is as an in-memory data grid that first might be used between your database and your application if your application team is building it, but could be used in other places as well. The way this works is the best of the in-memory data grids will be able to easily slide in between your application and your database and look like a SQL database. So there's some that are key value where you have to rewrite the application and rip out your SQL to have this read-through, write-through cache pattern, not a cache-aside pattern, but something that sits in between the path of all the transactions and the queries. At best, it gives you a JDBC, ODBC driver that the application can use to connect. And then at best, what it does is it acts as the new database. It connects to the database, inherits the SQL schema, populates the in-memory data grid, and then for every write, coordinates a write to in-memory and a write to the database, and for every read, because the data is now completely in sync with the database, can handle all the reads directly. So on the one hand, it's no rip and replace of MySQL, of your instance. It's still used as the persisted record. If the in-memory data grid goes down and it's all in memory, the in-memory data is gone. It needs to either be refreshed from the database or from a persisted local store. But MySQL is the transactional guaranteed backup of the data. It's in-memory speed. You can actually put nodes. You can partition your data completely horizontally. So it partitions using a shared nothing architecture with one write master per node. You can actually replicate and partition the data for each node co-located with each app instance and scale horizontally that way. People do that with APIs as well all the time. But the data can be local in memory with the application. So it eliminates the network as a bottleneck as well. And if you're not co-locating it with third-party code, you can actually push code to each node in the in-memory data grid using what's called co-located computing, or a compute grid that distributes the code and runs it locally and aggregates the result set. That's another way of minimizing network traffic. That's how distributed SQL is implemented. It allows you to sit as a single in-memory computing layer on top of multiple data sources, so you can merge data for things like new APIs or new apps. And you can make copies of the data and put them on new nodes, and the grid will manage that as well, so that you can put new workloads, new real-time workloads against up-to-date real-time versions, real-time copies of the data for real-time analytics or real-time machine learning and all kinds of other use cases like APIs. That's the benefit of an in-memory data grid. There are a number of vendors out there. If you want a comparison, here's a resource to a detailed set of charts and tables that show you the differences between them. The biggest differences are going to be how easy it is to slide in between the application and database. Does it support SQL? Does it support all the different options around ACID transactions? How does it scale? And does it support other in-memory computing use cases? These are going to be the things that you need to think about. And these comparisons have pretty much all the details you can possibly imagine around that. But in-memory computing, while it may start between the application and database, expands into other places. So on the one hand, it expands as an in-memory data grid and gets used with APIs. It expands in that you can turn on an in-memory data grid to be an in-memory database, or you can install an in-memory database to handle all the other data ingestion that may not be stored in MySQL. And you can bring that all together in the same in-memory computing layer. You can then run different workloads against that combined data. You can do streaming analytics and take in new streams and process them and combine them with this data at rest. You can do machine and deep learning training, model execution, and testing all at once in parallel workloads. And you can even reach into Hadoop. Some of the in-memory computing platforms have bidirectional connectivity with Hadoop to bring in historical data for real-time analytics, to run combined compute that kind of benchmarks the real-time data or measures it against historical results. And by moving it all into memory into the cluster, it makes that performance real-time. It's not bound by the batch-based performance inside Hadoop. So this is really how Apache Ignite evolved. It started as an in-memory data grid. We contributed it back in 2014. And since then, it has been evolving to support these other kinds of projects and sit as a common in-memory data layer on top. All the functionality is in Apache Ignite for doing this. What we've been adding as a company is commercial support for Ignite, as well as hot patching and global support and services, as well as enterprise features around security and deployment and monitoring and management, and some high-speed connectors for adding the speed, the scale, and the production readiness for some of the several hundred large-scale customers that rely on us for taking Ignite into production. Interestingly enough, Ignite is used the most with MySQL. Over 40% of all Ignite users, when we do different surveys like the in-memory computing survey, over 40% are using Ignite with, or tend to use Ignite with MySQL. They're using it to merge data across databases as well. So 2/3 of them are using 2 or more databases. 40% are using 3 or more. But MySQL is really the most common, partly because people are trying to look for that read scale as an in-memory data grid, and sometimes the write scale as well. So it gets used across as a common data layer as more and more projects get added on for merging the data together in memory and creating this new real-time layer that will support things like APIs and mobile applications to not just add the scale, but 10 to 1,000 times scale, but lower the latency. So ING Bank, for example, was a classic story where for mobile banking, their loads, a mobile user was 7 times the load of a web user who was more load than a brick and mortar bank customer. So their loads were growing 25% a year. In order to deliver the response to this they needed sub 100 millisecond responsiveness within the API every time for the mobile application. They just couldn't get there because they were going through a TIBCO middleware layer to multiple backend applications, getting the data, trying to merge it, do the join, and then surface the result. So they actually embedded on top of all their databases, mainframe, Cassandra, MySQL, Oracle, you name it, it's all there. They actually embedded the data in the APIs in GridGain nodes co-located with the APIs. That gave them the sub 100 millisecond latency support every time. It also gave them the ability to introduce new services. It gave them the flexibility that they were looking for. So GridGain gets used at all these different layers as an in-memory data grid, a database, for streaming analytics, and for continuous learning. There are all kinds of features that you should look at when you're evaluating this. There's ANSI 99 SQL support and ACID transaction support, because an in-memory data grid should just be able to slide in between your application and your database and look like a database, or slide into an API that's a data service and just take over the SQL. You need SQL support to make this kind of transition easy. You need also to be able to run other kinds of code and distribute code. You need co-located compute. I think that's a really important one as well. And so you're going to look at things like this as an in-memory data grid. And these are probably the major reasons why people are using Ignite on top of so much MySQL. With in-memory database support, you can actually turn on the persistent store at any time with the memory data grid, and start to keep 0 to 100% of the memory in memory, or data in memory, and 100% on disk, and that's SSD or flash or whatever you want to use to persist the data. You can use this as an in-memory data grid or as an in-memory database. It doesn't matter, but it's a way of backing up your data for persistence, for fast restarts and recoverabilities. This is how people enable 5 nines of recoverability with Apache Ignite using the persistence. It is a full-blown distributed SQL and key value database that does co-located compute at scale. So you can think of it as all the benefits of an in-memory data grid with the benefits of a distributed database rolled up together into one. There's some great stream processing in Ignite, which is why people use it for stream processing and why it gets used with Spark. It's got the broadest support for Spark for doing in-memory data management for Spark processing. But it also supports a whole bunch of other stream processing and streaming analytics technologies. The largest Kafka Confluent customers are also the largest Apache Ignite GridGain customers. There's some really large scale joint applications, joint streaming applications that are out there. And once the data is being streamed continuously into Ignite, you can run any kind of SQL or Java or .NET or C++ code for co-located compute, or do it with Spark and run Spark jobs concurrently across the cluster. There is bidirectional connectivity with Hadoop that you can use with GridGain for bringing historical data into GridGain and then running mixed historical and real-time data workloads against the data for real-time analytics. And there's also built-in machine and deep learning where you could run traditional machine learning like k-means or KNN classification or multilinear regression against the data in place without having to move the data. You can be running it across the cluster continuously, where you run the model training continuously, you run the model testing continuously, and you run the model execution against the live stream continuously against the same live stream, and get to machine or deep learning with TensorFlow, let's say, that you expect from a human being making decisions and changing how they make decisions on the fly. Without this kind of in-place machine and deep learning, you often have to wait hours to retrain against large data sets before you can improve your models. That's not how people work, and that's not what people are expecting from machine and deep learning. So you can do the streaming analytics, and you can do the machine and deep learning as well in place in this kind of architecture outside of MySQL, but directly against the MySQL data. That's pretty much what we had to talk about. We'll take questions if there are any questions. and I will leave this up to refer you to the In-Memory Computing Summit that just happened. We always have all the recordings, and there's one happening in November in Silicon Valley near the San Francisco airport and the Hyatt. So feel free to join to see some of the previous recordings from customers and vendors. It's a multi-vendor conference that we host. Or come and join us in November, and I'll leave these other resources up while we take some questions. So with that, I will actually go look at some of the questions. Okay, there are a couple. The first one was with clustering. What do you mean with read versus write versus data set scalability? So there, if you go back to, I'll actually go back to arrays. Actually, I'll leave it here and I'll just talk through it. A multi-master architecture, a single master architecture with group replication or with Galera, you have one master that takes all the writes, and then you have any number of replicas that can take the reads, as well as the write. The write master can take reads as well. In a multi-master architecture, any of the nodes can take reads or writes. So the read scalability is easy, meaning you route to any node that can take it. You don't have to coordinate. The write scalability is harder because the nodes all have to coordinate. Every node needs to be able to agree with every other node that the write should occur. It turns out that this creates an exponential need for an exponentially growing global cache to coordinate and an exponentially growing number of handshakes. So because of that reason, and Oracle RAC was the first actually to encounter this, you have a limit to the number of nodes you can have. I think the largest Oracle RAC instance ever is 128 nodes. That's not actually a lot of nodes. That's big. It's not actually large in the grand scheme of things. Ignite clusters can be thousands of nodes. Compute grids can be thousands of nodes. You will eventually get to that kind of scale, especially with APIs when you're scaling API architectures. So you need to be horizontally scalable in writes, where you have a shared nothing architecture so that there's one write master so they don't have to coordinate. And then for also for data sets where you can partition the data so that you get beyond the 64 terabyte limit of core InnoDB. You need to be able to partition to have masters and replicas spread out across enough nodes in such a way that you minimize your network traffic, because your network traffic in a distributed database is really the first bottleneck you hit. We're gonna have time for one more question. So let me pick it wisely. What do you recommend as steps for, I'm going to summarize a couple questions. What do you recommend as the easiest steps to add speed and scale? I think for speed, for me, it's pretty clear. You're probably going to lower latency outside the database with an in-memory data grid or something like that, either in between the database and the app or outside of the application towards the APIs, because that's where you need to lower latency. You always have to follow what's asking for low latency and deliver the data directly to that app or API. That's the only real way to do it. Otherwise, you are beholden to multiple network hops, multiple joins. It's not, you can't do it. In terms of scale, I would say this. I think adding multi-master clustering up front is the best thing to do in place of vertical scaling. It's going to improve your reliability. So if you are in a situation where you're thinking of throwing hardware at the problem and scaling MySQL up, my recommendation is don't do it. Go for something like, a drop-in Percona with XtraDB cluster, or look at, if you think you need some of the features of Maria, then look at Maria. But Percona is a drop-in Enterprise Edition, a drop-in MySQL Enterprise Edition equivalent with some great performance tuning. So I would look at Percona. And then also, if you really think you need to partition because of your data set size, you're either going to partition manually, which is okay if your data isn't shifting around a lot. If your data is shifting around a lot and you have multiple workloads, my recommendation is go look at Clustrix or Vitess. So maybe Vitess on top of Percona. It's still early days. I'd probably go to the Percona guys to see if that makes sense or not. But otherwise, you might look at Vitess on your own, see if it works, or look at Clustrix. Your other option is, if it's right scalability, you often don't have much of a choice. If it's data set scalability and it's just reads, then maybe you can scale outside the database. But for right scalability, you're probably looking at a Clustrix or Vitess first to see if it'll work for you. And then otherwise, you might be looking at manual partitioning last. So with that, I think I'm going to close it out. We've run late. We started late, but we ran late. I hope this helped everyone, and looking forward to, feel free, by the way, to send any information to info@gridgain.com or rob.meyer@gridgain.com if you have any comments on this, and looking forward to having you at the next webinar. So thank you very much.